Hello, everyone. This is Mike Ryan, Director of Sales and Marketing with TXRX. Welcome to our webinar series. This webinar, TXRX Solution Customization and Versatility, is our fourth webinar out of 9 that will run the rest of the year. This webinar will be 45 minutes. You will be muted, so please enter your questions into the question box. We will address those at the end of the webinar. Now I would like to introduce our presenters, Scott Galligan, our Inside Sales Manager, and Perry Carter, one of our applications engineers. Scott, please take it away.
Hello, everyone, and welcome to our webinar on customization and versatility of TXRX combiner multicouplers. Hope everyone is doing well and getting through these trying times. My name is Scott Galligan. I'm the Inside Sales Manager, and I'm here with Perry Carter, one of our team of applications engineers. He will be available to answer any technical questions you may have. I've been working at TXRX for over 25 years, and Perry has been here for more than 20 years. The purpose of the webinar is to discuss our ability to create custom, complex combiner and multicoupler systems, and to demonstrate our product versatility that makes the designs possible. We will start with an introduction and overview of the combiner multicoupler concept. What are they used for and the challenges facing you, the customer? We will do a quick review of the basics of the system building block components and the design process. Then we will take a look at 2 sets of examples in each of the VHF and UHF bands. We will show you a relatively simple system and a more complex system in each frequency range. You will see how some key factors will impact the complexity of the design and how TXRX's flexible product platform and our design software help us to customize the system to fit the unique needs of most any application. Combiners are used to combine transmit signals from multiple radios onto one antenna, and multicouplers are used to take a group of receive signals coming into the antenna and splitting them into multiple radio receivers. These systems are an important part of any LMR infrastructure, and they can make or break the performance of the network. So it's critical to design and install them properly. Customers like yourselves always face the challenges of making sure you have the best frequency plan for the application. In your decision process, you have to understand the frequency plan, understand the risks and trade-offs, especially if it's a VHF or UHF system. And of course, you want to have the lowest total cost of ownership, highest reliability in the hardware, and future-proof the system for expansion or modification. These are tough challenges. Through today's webinar, we are hoping to help educate you on what to look for when choosing a system. The first challenge is to do your best to get an ideal frequency plan. Later in the presentation, we'll show you what makes an ideal frequency plan, but basically you want to have plenty of separation between transmit and receive frequencies, and you want to be free of lower order intermodulation hits. That will have the biggest impact on the complexity, cost, and size of your system. Once you have the frequency plan, then you want to look for the right product platform and supplier who can work with you to provide with the best solution, whether it's a simple frequency plan or a difficult one. Before we look at designing a system, we'll discuss the cavities that are used as the building blocks for our systems. The first one we'll look at is the TPS cavity. It was patented by the company founder 40+ years ago, and it's still a workhorse in the industry today. The patent has expired, and some competitors have imitated the design, but the original TPS cavity is a TXRX product. The TPS cavity is the backbone of our combiner and is used to cascade multiple frequencies together. It has the characteristics of a bandpass cavity, but is designed to combine multiple transmitters together without an antenna junction or a large cable harness. The symbol on the top left is what you see in your system design drawing to represent the TPS cavity. The C1 in the circle indicates that it's the first cavity in line, and the 1.5 indicates the cavity is set for 1.5 dB of insertion loss. This filter is available in 6 and 10-inch diameter. The larger cavity will provide better selectivity. If you have a more difficult frequency plan, such as tight transmit-to-transmit spacing, this may require the use of a 10-inch cavity. The bandpass cavity has a classic bell curve shape, which passes a narrow window in the frequency domain and gradually rejects more as the frequencies are farther away from the center. This cavity is available in 4-inch, 6-inch, and 10-inch diameters. These cavities can be easily cascaded to achieve the total isolation required. Having multiple sizes of the same type of filter becomes really beneficial because we can use the smaller 4-inch cavities if less isolation is required than the larger filters will provide. The 6 or 10-inch filter is adjustable by using the 2 tuning rods with the black plastic caps. One is the coarse adjustment and the other is for fine adjustment. We can shape the filter curves to widen or narrow the passband, increase or decrease the rejection, which is the slope of the skirts. Also, we want to bring to your attention the aluminum cavity itself. The 6-inch cavity shell used in each of the filter slides are identical. The connector loops are the magic that transforms one cavity filter type into another. An electromagnetic field is created inside the cavity when an RF signal travels from the input port to the output port. The metal shell serves as an electrical ground, which, while the shape and size of the orientation of the thin metal loop under the connector plate determines the filter curve, as you can see in the graph on the left. By changing the connector loop to a different type, we can produce different filter curves. This design greatly improves the flexibility of our product family and is one of the key advantages of the TXRX filters. This is our vari-notch cavity. This cavity's response curve shows that it can pass a specific frequency and reject a specific frequency. It's a different useful feature in a combiner. It's a very useful feature in combiner multicouplers because it's all about passing the desired frequencies and rejecting the undesired frequencies. The symbol at the top left shows the insertion loss to be 0.3 dB, and we expect to get around 40 dB of isolation at the deepest notch. The schematic also specifies the frequency we are trying to reject, 174.6840 megahertz in this case. It's also available in 4-inch, 6-inch, and 10-inch diameter cavities. The smaller 4-inch vari-notch is useful because it can be strapped to a larger cavity so that it doesn't require any additional rack space. Here you see the same 6-inch shell being used, but we only need to use one loop plate with multiple connectors on it. The unused loophole is covered using an aluminum disc. The series notch cavity is another type. It rejects a specific frequency with a fairly wide passband. This is used for very closely spaced pass to reject frequencies. As you can see on the top left picture, indicates the loss is 0.95 dB and the rejection is 20 dB at the intended notch of 159 megahertz. This cavity is available in 6 and 10-inch versions. In summary, we just reviewed the several types and sizes of cavities. Most of them are round cylindrical shape and are available in 4-inch, 6-inch, and 10-inch diameters. We do offer square cavities for special applications. There are 4 unique types of cavities based on their performance curves. Each serves a distinct purpose in passing certain frequencies and rejecting certain frequencies. It's like a carpenter's toolbox, a chisel, a hammer, a screwdriver. They each have a unique purpose. By combining the right mix of these cavities with their different sizes and types, we can optimize each design for almost any frequency plan. Now that you have the basic knowledge of the system's building blocks, we'll take a more in-depth look at the actual system designs examples. Before we look at the examples, let's discuss some design considerations to take into account. My colleague, Jim Grotke, had discussed these design process in more detail in a previous webinar, so we'll only skim through this as a refresher. After you have the frequency plan, the first step is to make sure that there are no harmful IM hits. IM stands for intermodulation, and they are generated when multiple high-level transmit signals mix together with each other or with each other's harmonic frequencies. The resulting IM products, if they are very close to a receive signal, can easily overwhelm the receiver and disrupt the system operation. Therefore, it's critical to do IM study and make sure that there is no IM products that could interfere with your receive signals. If there are, you may have to go back to the frequency coordinator and ask for some new frequencies. The next consideration is how many antennas you will use for the system and how they are placed on the tower. The rule of thumb is that the more antennas you have and the farther apart the antennas are, the better isolation achieved. But you're likely to be constrained by cost or other practical considerations, such as the available space on the tower. You should have at least one TX and one RX antenna. Single antenna systems are possible, but it will significantly increase the risk and complexity of the system. Once the frequency and antenna configurations are set, then the actual design process is fairly straightforward. The main goal is to protect the RX signals from either the IM or the sideband noise of the TX signals themselves. Remember, a typical TX signal is about 1 trillion times stronger than an RX signal. Yes, 1 trillion, 12 zeros. So it's very important to provide all the protection you can for the received signals. The actual design process by TXRX engineers is done with the help of a TXRX design software package, which was the topic of the previous webinar on what we call the toolkit. The key functions we perform are generating the IM study, plotting the spectrum DNA graph, calculating antenna isolation, and then following the isolation matrix or isomate to decide how much filtering is needed for each channel, and then choosing the right cavity from thousands of curves in the TXRX toolkit library. Now we will take a closer look at two sets of examples with simple designs versus the complex designs. As I mentioned earlier, the biggest contributor to a system's complexity is the frequency plan. The most important thing to look for is the guard band, which is defined as the spacing between the closest TX signal and the closest RX signal. Other important factors are the TX to TX spacing and the TX to RX antenna isolation. In general, the greater or larger these three numbers are, the easier it is to design a system. Here's an example of a simpler VHF combiner multicoupler. As you can see, there's a nice TX to RX separation as well as TX to TX separation. There's a 3.878 megahertz guard band between the TX and RX frequency. That is what the spectrum drawing on the left is showing. The red lines indicate the TX frequencies, and the blue lines the RX frequencies. With such a wide guard band, it's very easy to achieve the isolation required, which is accomplished with just three TPS cavities per channel. The TPS cavity does the job of both combining the three frequencies as well as providing the necessary filtering on the TX channel. The receiver side is also relatively simple, just one bandpass filter consisting of four 4-inch bandpass cavities. The reason we need the 4 cavities is to achieve a wide enough bandwidth to cover all the RX frequencies. Here is a very different VHF system. It has only 2 pairs of frequencies, but the guard band between TX and RX is very small, only 150 kilohertz. The graph on the bottom shows the isomate. As I mentioned earlier, isomate is short for isolation matrix. It is a set of formulas that determine how much isolation or filtering is needed for each frequency. For the TX channel that is closest to the RX channel, we have to provide at least 100 dB of isolation. The antenna isolation between the TX and RX antennas was calculated to be 32 dB. So that means we need to have 68 dB worth of filtering. It took 5 cavities to achieve this. On the other hand, the better spaced TX frequency doesn't require as much isolation. So the isolation requirement was met with only 3 cavities. That's why it's so important to have the flexible platform, so we can add just the right number of cavities with the appropriate combination of filter types to achieve the desired isolation. The receive side of the same system is also very complex. The RX channel that is closest to the TX frequency requires 6 cavities to meet the isolation goal. All of that is due to the fact that the TX and RX guard band is narrow and the antenna isolation is minimal. They are installed horizontally, not vertically. Fortunately, because the TX-RX has a software tool to calculate exactly how much filtering is needed and a vast library of filter configurations to choose from, our engineers can pick the best combination to meet the requirements. No more, no less. Here is an example of a 4-channel UHF system. The frequency plan is pretty much ideal. In UHF at 450 to 470 megahertz, the TX and RX pairs are 5 megahertz apart. In this case, because the TX and RX groups have decent spacing, it provides a large enough guard band of 2.775 megahertz. So we only need to use a TPS cavity on each of the transmit channels and a single bandpass preselector on the RX side. Alternatively, for this frequency plan, we can offer a compact combiner with integrated power monitoring. This compact design requires only 7 rack units in a 19-inch rack. Picture shows not only the combiner, but also the recommended transmit filter for this and the digital power monitoring as well. The block diagram shows the system connectivity. The compact combiner is not customizable. You cannot add additional notch cavities to the channels, but if you have a relatively simple frequency plan and a small footprint is your top priority, along with the power monitoring capability, this is a perfect choice for you. Here is a complex UHF frequency plan. Similar to the VHF example, the guard band is narrow at only 500 kilohertz. As you mentioned before, the UHF frequency plan, the frequency pairs are 5 megahertz apart, but because these frequencies are spread out wider, the guard band is narrow, and as you can imagine, it makes the design more involved. Here is the system drawing. The transmit channels are closer, so the RX frequencies need a lot more cavities. The transmit channels that are closer to the RX frequencies need a lot more cavities to filter out the sideband noise. The RX channels can still fit in one window filter, but they need to have additional notch filters to protect against the transmitter frequencies and protect the receive amplifier from being overwhelmed and desensitized by the strong TX power level. In summary, combiners and multicouplers are important parts of the LMR network. They can be very simple or very complex. The number of channels isn't always the biggest factor in cost. A difficult 3-channel system can cost 10 times as much as a simple 6-channel system. As a customer who is deploying a system, the most important thing to consider is the best frequency plan for your application. Once you have the site information, please work with our design team at TXRX. Our versatile platform with different types and sizes of filters, along with the help of our software design tool, allows our applications engineering team to choose the most appropriate filters for your needs. We don't mean to brag, but there is a reason TXRX has been an industry leader in the LMR RF conditioning business for more than 45 years. Our ability to optimize a system solution for each unique application is second to none. And let's face it, every RF system is unique. So you can never go wrong with choosing TXRX Systems as your partner and supplier for combiners, multicouplers, or many other filtering needs. Hopefully this webinar was informative, and we look forward to working with you for your design needs. Please enter your questions in the question box and we'll get them answered. Thank you very much.
Thank you, Scott. Can you see the questions okay? Otherwise, I can read them out to you.
Let's see.
Oh, while you're looking for them, here is the first one. Is there a difference in power handling depending on the cavity size, 4-inch, 6-inch, 10-inch?
Well, the 6-inch cavities will handle more power, and the 10-inch cavities will handle more power than the 4-inch. There is a little bit of power difference, not a big difference, but the heat dissipated by the bigger cavities will help handle higher powers.
Okay, thank you, Jim. And another question, how do you handle high power for 3/4 wave cavities where the center conductor gets hot?
Well, for the most part on that, if the center conductor is getting hot, I think I'd want to look and make sure that the center conductor and all the connections are proper, because it almost seems like that something might be giving some reflected power to increase that heat. It's more of the loops that you're really worried about as getting hot. The center conductor shouldn't get that hot. Well, yeah, we do have internal temperature compensated cavities as well to help when you have higher power applications too. I'm just a little bit concerned about hearing the high temperature on a center conductor. It almost indicates some sort of connection issue.
Okay, and then the next question, how do you expand a system with one or more channels?
Okay, what you do with that is essentially it's put together in such a manner that you would add the channels to the, if you recall the drawings, where you have the cavities stacked on top of each other up to the antenna. You would disconnect the antenna connection and put your new cavities in between the existing system and the antenna in most cases. That's generally how it would be done.
Okay. Are there any other questions out there? We can wait a couple minutes for other people to ask questions. We're ahead of schedule. Okay. Well, then I will close the webinar. We appreciate your attendance and your questions. I will email a link to the webinar within the next couple of days, and then also look for the invitation for the next webinar that we'll be having 6 weeks from now. And Scott and Perry and Jim, thank you for your presentation, and that will be the end of our webinar. Thank you, everybody. Goodbye.
Thank you.